Hello again, students. Last time we looked at three of our four new special types of random variables. We looked at the binomial, the Poisson, and the exponential. And now we'll look to the last one that we'll be looking at this time anyway. And it's called the normal distribution, or the bell-shaped curve. We've all had some type of dealings with the normal distribution before. When students ask me, do I grade on the curve? No, I don't. And the implication is it's the bell-shaped curve, the bell distribution. The most commonly seen application of the normal distribution is, of course, IQs. IQs of people in the United States are roughly normally distributed. They roughly take on the bell-shaped curve. And the mean value or expected value used to be 100, but it's below 99 now. We're not getting smarter, friends. we're not, as you can see by the politicians we elect. Very sad. And with a standard deviation of, it's really 16. The Stanford-Binet IQ test, which is the most common one, has a standard deviation of 16. But we're going to make it 15 so it's easy to work with. So IQs are stated to be normally distributed with a mean value or expected value mu. So now we're going to use the term mu, the symbol mu here for the expected value. Before we've used E of X, E of capital X. But for the bell-shaped curve, it's come down that it's just practice that E of X is correct, but we use the symbol mu to represent the average or expected value. And we use the standard deviation instead of the variance to measure its variability. So, given that we have a normal distribution with a mean of 0 and a mean of 100 and a standard deviation of 15, first thing we would do is to draw that curve. Here's how you draw a curve. You don't start at one end and go up and down because it never comes out symmetric. You start at the top and draw the left side, and then you go to the top and you draw the other side, and then you got a shot that's going to come out symmetric. You try and go ooh like that, and it never comes out symmetric. So if we have a random variable that's normally distributed, and you tell me the mean is 100, okay, that's where it peaks out. So first thing I see is that I've drawn a continuous line, so that IQs must be continuously distributed. Well, our convention is to round them off to the nearest IQ point, but if we gave you like a 10,000 question IQ test, we could measure it to several decimal points. So, in theory, that IQs are continuously distributed, but we only measure them to the nearest IQ point or tenth of a point by convention. But for the normal distribution, we are assuming that our random variable is continuous. Probability on the whole curve is 1, of course. So what's the probability that we grab somebody that have an IQ of 100 or less? 0.5, half the curve. What's the probability they have an IQ of 100 or more? 0.5, half the curve. Now, you see this point where it goes from being an upside down bowl to a right side up bowl right there, where it goes from being concave to convex. It's convex and then concave and then convex. Right side up bowl, upside down bowl, right side up bowl. That point right there, called a point of inflection, is exactly 1 standard deviation away from the center point or mean. And go the other way, exactly 1 step, 1 space of 15, 1 standard deviation away from the mean to the right, and you've got the second point of inflection. And if you look at the area between 85 and 115, it's a big chunk, well over a half. So half the time we're being, over half the time, 85 and 115. We are within plus or minus one step, one standard deviation of the mean, well over half the time, as we'll see. All right, so we're good to go. What's the probability that we grab somebody and they have an IQ of 85 or less? For some reason we want to know, maybe it's the minimum to get into the services. I think it's around 85 to get into the service. For some other reason we want to know 85 or less. So who's in this group? Politicians, my brother-in-law and his whole gene pool. They're over here. Yeah, a few other people I don't want to mention because I don't want to get sued. But you know, these are not the brightest people on the planet here. Little known fact, what was Forrest Gump? Little trivia question. What was his IQ? I think it was 70. I think it was around 70, 71, 72. Right over there, you know? Because my little known fact, my brother-in-law was the technical advisor on the movie Forrest Gump, the early years, because they needed somebody who could sound stupid. And you know, they want to know how dumb people act. So my brother-in-law was the technical advisor. Movie Forrest Gump, the early years. Oh, less than or equal to. Well, geez, that's direct table lookup, right? Same as everything. True. So we head to our tables provided by our dear and beloved prof and all-around swell guy. And on page T12 and 13, we find the cumulative normal distribution. Okay, and when we go to each new table, we look at what are the column headings on the table, because that's what I got to match up with. I got to match up with a Z value. What's going on? Is Zorro been here or something? What is a Z value? A Z value is, well, out of all the infinitely number of large normal distributions I have out there, what would be the world's easiest one to work with? The world's easiest normal distribution to work with is the one with a mean of 0. 0 is even easier to work with than 1. And what would be that's the world's easiest mean to work with. What's the world's easiest standard deviation to work with? 0 would be the easiest standard deviation, but then it wouldn't be a random variable, it'd be a dot. It's 1 is the easiest standard deviation. And the beauty of it is, how many ever standard deviations you step off, that's the Z value. So if you ever get a technical printout that's got some numbers on it as a Z value column, that is how many standard deviations you are away from the mean. The Z value is how many standard deviations you are away from the mean. To get to 85, give me road directions. Start at the mean, hang a left. To get from 100 to 85, start at the mean, walk 15 IQ points to the left, which is what? How many standard deviations? 1. 1 negative. The sign is exceedingly important. -1. Okay. -1 on this curve has the exact same area below it as 85 does on this curve here. So we head to our table, look up -1.00, -1.00. I got it. Aha! Right there. 0.1587. So the probability of you grabbing somebody off the streets and they having an IQ of 85 or less, about 16%. What's the probability we grab somebody off the streets and they have an IQ of 115 or less? All right. Less than or equal to? Ready to look up. Just give me a Z value. How do I get from 100 to 115? I walk an additional 15 to the right. I walk +1 standard deviation. plus 1. And that takes us to our second table for the normal. Okay, on page 12 is when we walk to the left of the mean. On page 13 is when we walk to the right of the mean. Okay, the one on page 12 starts basically at 0 and goes to 0.5, right? If we step way over to the left and walk to the mean, eventually we're going to get to 50% of the area. And then the table on page 13 starts at 0.5 and gets bigger, 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 and finally goes to almost 1. And we're looking at less than or equal to probabilities, probability being to the left of us. And so when we look up plus 1.00, be careful because the hundredths change depending on whether we're walking to the left or the right. The order up here changes, so just be careful. And 0.100 is 0.8413. So probability being 115 or less, 0.8413. What's the probability being between 85 and 115? Take 115 or less, minus 85 or less. We got those values here, 0.8413, 0.1587. And the answer was 0.6826. Normally, I don't care about the actual answer to the problems, as you've noticed. In this case, I do. Memorize that number. How many times this semester have I said the word memorize? Never. Memorize that number. Instead of that crap you're tattooing over all over your body, tattoo this one here. Okay? 0.68. 0.68 is good. 2/3 or 0.68. Okay? I guarantee that if you know these three things, I'm going to ask you to memorize for the rest of your lives, that you will be able to impress someone somewhere in your life when you know these. It will come up. I guarantee. I get emails from former students virtually every semester. I had you 30 years ago. Are you still using that? I leaned over problem. Yes, I am. I've been using some of them a long time. And they said, yeah, I had you. I thought you were a creep, but I learned a lot, and I was able to secure this job. I've had students nail jobs on the spot because they could cite those values. And the values we're citing are plus or minus 1 standard deviation. Happens 68% of the time. 68 or 2/3 works. You're within plus or minus 1 standard deviation of the mean 68% of the time. You're within plus or minus 2 standard deviations 95% of the time. And that's the standard in industry. When we forecast, we put 95% confidence intervals around our forecast. We walk plus or minus 2 standard deviations. It's pretty much the standard in industry. And I pretty much bet my job I'll be within plus or minus 3 standard deviations of the job. It's 0.99 and a lot of change. 0.68, 0.95, 0.99, plus or minus 1, 2, and 3 standard deviations. I will assume you know all of those for the rest of the semester, and you've memorized them for the rest of your lives. All right. And lastly, you want to join Mensa. Okay. Mensa is the society of people with high IQs. Okay, and in order to get into Mensa, you need to be in the 98th percentile of IQs. That's their threshold to get into Mensa. You want to think you're a candidate for Mensa, and you know your IQ, then I'll tell you whether you can get into Mensa or not. Mensa comes from I think a Greek word that means table. That anybody, they meant by it was anybody who's smart is welcome to sit at the table. We don't care, what your economic background or whatever is, that as long as you're smart, we'll welcome you. What does Mensa mean in Spanish? stupid. So the Mensa group in Mexico, somebody look it up for me if you would. What do they call the Mensa group in Mexico? Because I don't think they call it Mensa. I would think not, but it's stupid in Spanish. All right, so we want to get into Mensa, and we want to know, are we in the 98th percentile? Do we have an IQ that's greater than or equal to 98% of the people in the US or the world? So this is the second way to use the table that's legal in California. The first way, you give me the number of standard deviations stepped off. I look up a probability, right? What's the other way? Exactly the opposite. You give me a probability, I tell me how many standard deviations you got to step off. That's called a percentile. So we head to the table, say, what is the first one bigger than or equal to 0.9800? Okay, obviously I go to page T13 because we're going something bigger than 50%. 98% is bigger than 50%. And these values get progressively bigger. So we go down, we start reading. Oh, I'm getting warm, I'm getting red hot. Ooh, 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 ooh. Oh, too far. 0.9821. Back it up. Start going across. And we stop when we find the one closest to, no, first one bigger than or equal to. All of our percentiles will be, I think, bigger than 50%. So it's first one bigger than or equal to. We take the one that exceeds it. I would not mark it wrong if you chose the 0.9798. The correct way is 0.9803. That is the first one in the table that is bigger than or equal to 0.9800. We need to step off 2.06 steps. 2.06 steps. So start at the mean. I don't use any formulas or anything. I use common sense. Start at the mean. Walk off 2.06 steps. And here's where most students miss out. They just leave it 100 plus 2.06. No, it's 2.06 steps of width 15. 2.06 steps of width 15. And this is how, of course, you'd leave it on the exam, 100 plus 2.06 times 15. That turns out to be, I think it turns out to an IQ of 132, because again, we simplified sigma and used 15 instead of 16. So I think if you want to get into Mensa, you need an IQ of 132. All right, so that's the normal distribution. That's everything we need to know about it. Okay, we need the normal distribution for the second half of the course. We need all the others for the first half of the course. After the midterm, though, we will not any longer use the binomial, Poisson, or exponential, but we will be using the normal throughout the course. The normal distribution was first recognized by our old buddy Galileo. He was the guy who he didn't invent the telescope, but he was the first one to actually look at the skies at night with a telescope. And he said, hey, there's these orbs that are going around Jupiter. They're orbiting Jupiter. You know, and before that, everybody said that there was the crystalline curtains above that were going around the Earth. And then Copernicus came along and said, no, the Earth rotates around the sun. But Copernicus also, he wasn't that bright. He also thought the entire universe revolved around the sun. So he wasn't. On my list of top 10 smartest people that ever lived, Copernicus ain't there. So Galileo had a bunch of people working for him, and he was tracking the positions of the stars and the planets, you know, and they had a coordinate system. And he noticed that each night he'd have different people figure out where the planet was, and they really didn't move, but he still got different measurements, just slightly different, a little bit less, a little bit more, and he plotted them, and they took this bell-shaped curve. So a common application of the bell-shaped curve is it's errors. If you have a machine that's filling up like a box of Wheaties, they're not all the box of Wheaties don't weigh exactly the same. You're putting in flakes, you know, so a little bit less, a little bit more, and it takes on a roughly bell-shaped curve. Then Gauss and Laplace came and actually derived the formula as we see it down here. It happens a little bit in industry, but I cannot say X equals something like I can for the other three. Okay? You have to be told on the midterm exam if something's normal. The other three, you got to figure out what it is. But if it doesn't say normal in the problem on the midterm, it ain't normal. Second half of the course, you'll figure out on your own whether it's normal or not. But for the midterm, all right, so now you know everything. Let's just do one more problem and we will adjourn for another fun-filled weekend and week. Our practice problem is page 10, number 13. Fredericks of Siberia. Little known outpost of Fredericks. Remember Fredericks of Hollywood? I think they closed all their stores. I don't know. I mean, personal knowledge. In fact, they send me several catalogs a year. Doesn't mean I've ever bought anything from them. Anyway, Fredericks of Siberia, we do sexy night garments. And monthly demand is normally distributed with a mean of 2,000 and a standard deviation of 100. What is the probability of that? As we will see in the second half, we want to predict or forecast things that will happen, and we take samples in order to do it. And when we take samples of over 30, we get, by some magic, this normal distribution. So in the second half of the course, we deal with sampling, additional market research, sampling, and it turns out that we need the normal distribution, that once we sample to make predictions, that our predictions are normally distributed. So we're told that demand next month is bell-shaped, centered at 2,000 with a standard deviation of 1. And immediately when I see a curve like that, click, automatic. Just automatic reflex reaction. Got a bell-shaped curve, centered at 2,000. 50% chance it's greater than 2,000. 50% chance it's less than 2,000. What else do you know? 68% chance it's between 1,900 and 2,100. 95% chance it's between 1,800 and 2,200. Oh, that's part B. Part B is that. There you go. The answer. Midterm exam, 3 weeks from today. Problem 1A will be answered by 0.68, 0.95, or 0.99. You write anything else, you look it up, you do anything else, I will mark it 100% wrong. I'm throwing you a gift. And the first problem, 1A, the answer is 0.68, 0.95, or 0.99. It'll be a plus or minus 1, 2, or 3 standard deviation example. You are to write that, you work it out, I will mark it wrong because you didn't memorize the probabilities like I asked you to. Okay? I'm not just fooling around here, folks, okay? When I tell you to memorize it, it will be useful in your life. Okay, you're sitting, you're next to whoever you're engaged to, talking to their parents or something on TV, and it said, we did a political poll, and boom, and they give you the error factor, and you can make a nice statement, so that's a 95% confidence interval. Boof. Yeah? Not too often you get a chance to impress somebody with your intellect. Okay. Know these. All right, so there's a 95% chance we're between 1,800 and 2,200, and then there's a 99% chance I'm between 1,700 and 2,300. Okay, what else do we know? Well, between 1,800 and 2,200 is 95, right? What's left? I've accounted for 95%. What's left? 1 minus 0.95 is 0.05, right? Okay, split it in half. Half is to each side, splits it equally. So you also could say, well, the probability of being less than 1800 is 0.0025. And the probability, there's an extra zero there, sorry. Extra zero, no good. 0.025. And the probability of being above 2200, 0.025. What's the probability of being 2200 or less? What's the probability of being 2200 or less? Okay, so 1 minus 0.025 is 0.975, or 0.95 plus 0.025, 0.975 again. Yeah, 0.975. So we know a lot by knowing those three plus or minus 1, 2, and 3 standard deviation values. I want to know what's the probability of being between 1850 or less. 1850 or less. Okay. So on the exam, you should just be able to eyeball these, but I start at the mean and walk, what, 1, and gets me to 1900, another half. 1.5 to the left. Or you can work it out if you want. Hopefully you'll be able to eyeball them on the midterm. I walked 150 to the left. How do I make 2000 into 1850? You subtract 150. Divide by the width of your standard deviation, 100. Oh, that means you walked 1.5 to the left. 1.5 to the left. 1.5. 1.5. 1.5. 0. 1.50. 0.0668. And how many units should be stocked if we want to be 95% sure we have enough? Did we just answer a 95%? Oh, that's a 95% probability interval, or sometimes called a confidence interval. Here's what I do when I forecast. I do this. I think we'll be 2000. Best guess, worst case 1800, best case 2200. 95% chance we'll be in between. If you ask me to actually make a decision using it, how much should we stock? Okay. A forecast is a 3-number answer. I think it's going to be 2000, could be as low as 1800, could be as high as 2200. That's the interval, confidence interval or probability interval. Okay. If you ask how many should I order or produce so I'm 95% sure I have enough, that's one number. That's a 1-number answer. When you call the factory foreman and say, hey, make X number, and the foreman asks, how many should I make? And so I'm 95% sure you have enough. We give them one number, one and only one number. And it's just a straight percentile, a straight percentile. Okay. The 95th probability interval, we look up the 2.5 percentile and the 97.5 percentile, leaving 95% of the area in between. On a straight 95% percentile, we just look up 0.9500 in our table, 0.9500. Here we go, 0.9, going down the table. Oh, too far. 0.9554, back up and across. Oh, first one bigger than or equal to 0.9500. 0.9505, 1.65, 1.6, steps away from the mean. 1.65 steps. Start at 2,000, your center point or mean. Walk 1.65 steps of width 100. Tell the head of the manufacturing facility to make 2,165 garments for next month. And you're 95.05% sure you got enough. Okay, in the second half of the course, we will be using this notation. Second half of the course is a straight cookbook part of the course. It'll give you a Z and then a subscript. What that means is head to the normal distribution. C says go to the normal distribution. And then whatever's in the subscript says look up that percentile. So that's about it for the second half. Formulas will tell us exactly where to go, and it's much more cookbookish. So head to the normal distribution, Z, look up the 0.9500, and the closest one we can get is 0.9505, and that is 1.65 steps away from the mean. All right, have a gander, practice problems at number 14 and number 17. I will see you next time. Not to shatter your confidence, but the next lecture is probably the most difficult of the entire semester. So take your whatever stimulants you need, your 5-hour energy or whatever before you show up. Hold on. Yes, sir.